In this video, we're going to be exploring the photoelectric effect and the properties of photons. It should be a pretty short one, since we're just going to go over some definitions and then two equations you need to know. This picture on the right shows light, which as you know travels in a wave, and this wave is made out of these little things, which are known as photons. So again, light is made up of photons, and photons carry energy. If the conditions for absorption are favorable, then an atom can absorb a photon. For this absorption to happen, the energy of the photon must equal the difference in energy between two electron orbitals. If the atom absorbs the photon, then our electrons will become excited, meaning that they will occupy a higher energy state. And then when our electrons inevitably return to their lower energy state, the atom will eject a photon of equal energy. So this little box down here, these two notes over absorption and ejection, is really what you should take away from this little review. If you're confused over any of this, in my last video, the one that comes right before this one, I went into greater detail over photons and their absorption in atoms. So I recommend checking that out if you really don't know what's going on right now. Moving on to the other part of this video, there are two different equations we can use to describe properties of photons, and they are as follows. The first is called the energy-frequency relationship, and it reads E equals kind of a curvy h times nu. E stands for the energy of a photon. This curvy h is Planck's constant, which has a value of 6.626 times 10 to the negative 34th joule seconds. And the Greek letter nu represents the light frequency. In chemistry, you're going to be presented with problems in which you either know the energy of a photon or you know its frequency, and then you just have to solve for the other variable. The second equation is called the speed of light relationship. It reads, this cursive c equals lambda times nu. The cursive c here stands for the speed of light, which is 3 times 10 to the 8th meters per second. That's the speed a photon travels at in a vacuum. Our lambda denotes the wavelength of the light. And again, nu denotes the frequency of our light wave. Again, you'll be presented with problems where you only know one of these variables, such as you only know lambda or you only know nu, and then using algebra, you just have to solve for the other variable. Let's do two example problems now using each one of these equations. This first problem reads, a certain photon of light has a wavelength of 450 nanometers. What is the frequency of this photon? So because the wavelength of the photon is already given to me, and I need to find its frequency, I'll be using the equation, the speed of light equals the wavelength of the photon times its frequency. And now I just have to plug in what I know. The speed of light is 3 times 10 to the 8th meters a second. The wavelength of this photon is going to be 450 nanometers, and then my frequency is what I'm solving for. Something I have to do though before I can divide, this is in meters and this is in nanometers, so I want to change my wavelength to meters. Putting the prefix nano in front of meters just means that we're multiplying it by 10 to the negative 7th, so I'll do that. And now I can rearrange and solve for frequency. My meters will cancel out, and I get a final frequency of 6.67 times 10 to the 14th per second, or another way of saying that is 6.67 times 10 to the 14th hertz. As you can see, pretty easy problem. Let's do one more of these. This problem reads, a beam of light has a frequency of 6 times 10 to the 14th hertz. What is the energy of a single photon in this beam? And so because I'm given frequency and I need to solve for energy, I'll be using the equation, the energy of a photon equals Planck's constant times the frequency of that photon. And now let's just plug in what we know. Remember that Planck's constant is 6.62 times 10 to the negative 34th joule seconds. And in this problem, my frequency is 6 times 10 to the 14th hertz, or per second. So my seconds will cancel out, and I can now just multiply these two values by one another. And I get a final answer of energy equals 3.97 times 10 to the negative 19th joules. So as you can tell by now, the actual calculations for photon problems are extremely simple. Just make sure you know how to use these two equations. And with that being said, that's all you need to know about the properties of photons for chemistry. If any of this didn't make sense, I recommend rewatching parts of the video. If it's still not clicking, take a break and come back after. Thank you for watching.